Okay. All right. Well, hello, everybody. I'm Jared Balbona, and I'll be talking about estimating the effect of vertical transmission using structural equation modeling. So I'll kick things off with an example. Let's say that this is you, and that you really enjoy violent, horrifying, scary movies. You just can't get enough of them. They bring you joy. And let's say that your parents also enjoy these same kinds of movies. Now, there are a couple explanations for why this might be the case. The first is that something inherent in your genome predisposes you to love these. Maybe it's through some kind of neurobiological or behavioral pathway, but you just came pre-programmed with a love of the genre. And because your genes were inherited from your parents, maybe they possess these same genetic factors, and which results in the same phenotypes for them as well. So this is a direct effect. Your genes are directly impacting your biology or behavior in some way, and it's not being mediated by anything. So that's one option, but let's consider an alternative. Maybe you really love these movies because a big part of your upbringing was waking up on Saturday mornings and you and your dad would get together and watch like Saw together. And maybe at night before bed, you and your mom would watch the Texas Chainsaw Massacre. So maybe this was even a trait that your parents bonded over when they first met. And maybe it was something that they did with their parents, and so on. So this is vertical transmission, or the process by which a parental phenotype directly influences an offspring phenotype. In a sense, you're inheriting this environment from your parents, and as such, teasing apart these inherited environments from these inherited genetic factors has historically been really difficult in our field. So to date, the best attempt at separating these effects has come from Kong et al. In 2018. Using trio data, they looked at the following. So here we have the alleles that your father transmits to you, and the alleles that your mother transmits to you. These form your whole genome, which in turn influences your phenotype. Similarly, the alleles your father does and does not transmit to you form your whole genome, same for your mother, which influence their phenotypes. So we have these three direct effects, and in addition, we have this vertical transmission pathway where your parental phenotypes are directly impacting your phenotype. So taken together, the Kong et al. Paper was really innovative because it looked at how the relationships between all these different factors, and in particular how the relationships between the non-transmitted alleles with the offspring genotype and phenotype, how these all relate to each other. And in doing so, we're able to quantify algebraically the effect of what they call genetic nurture, but what is better known in our field as passive GE covariance. So while this was innovative, it was not without its faults. No approach is. First, they assume no assortment beyond the parental generation, which may be true for some traits, but for a large number of other traits will be untrue or difficult to evaluate. Secondly, while they had all the tools to estimate the effect of vertical transmission, they only estimated the effect of passive GE covariance. Third and finally, they derived a lot of their math from scratch, so it only applies to the case in which they derived it. So you can't extend their model to other situations, like if you were to have data without trios. So to address these concerns, we built a structural equation model of their logic that, one, properly accounts for assortment. Two, using only a polygenic risk score, can obtain a full estimate of familial environmental variance and variance due to vertical transmission, which is really exciting. We can accurately estimate how important parents are for their children's phenotypes. Three, it's super easy to use. You don't need to be any kind of structural equation modeling expert. And fourth and finally, it allows for a vast number of extensions that can best fit the trait and data you're working with. So if we move back to the schematic from Kong et al.'s paper and rearrange the parts, head on error terms to account for everything not included elsewhere in the model, and throw on some path coefficients, we now have a structural equation model of this direct effect. So this model does not include vertical transmission or assortment in it, but I think it's still a useful starting point before getting into the models that I'll talk about later. So here we have these deltas, and these are akin to regression betas. As with most of the letters that I'll mention, they represent the same thing in our model as they do in Kong et al.'s algebra. So you see that the transmitted alleles have the same effect on the offspring phenotype as the parent phenotype. We also have these double-headed variance arrows constrained to values of k. Now k is a constant, it's not an estimate, and its value is decided upon based on how and when the haplotypic variances are scaled. Now finally, we have this environmental component that I mentioned earlier. So if we take this model and we want to add in vertical transmission, it's not too hard. We just have to add in these three parts. So we have these three big Fs, each representing familial environment and each with a variance of X. And because these polygenic risk scores might be capturing some of the effect of familial environment and vice versa, we also have covariances that equal half W. Finally, we have the vertical transmission effect of F. So that's the effect of the parental phenotype on the offspring phenotype. So for this model, if we want to include assortment, that's also easy to do. So this is the model with assortment, model 2. It looks similar, but we're adding in a covariance between haplotypes, you can see here, and slightly altering the variance within haplotypes, and I'll explain why. So if we have this offspring genotype with 2 loci, after 1 generation of assortment, you'll start to see correlations between the different haplotypes. So your father's alleles, the alleles from your father will be correlated with the alleles from your mother. And this makes sense. But after more than 1 generation of assortment, you also start to see correlations within haplotypes. So maybe the alleles from your grandmother are correlated with the alleles from your grandfather. Maybe it's a great-grandparent, who knows? But for that reason, we now have this G covariance between haplotypes and a G component within haplotypes. We're also adding in this copath, which is used in structural equation modeling to model assortment between mates. And it has some unique properties. So as people who do structural equation modeling know, there are a set of rules that dictate how you can trace a path from one variable to another. However, once you cross this copath, all those rules reset. So for example, if you go through a double-headed arrow, which in path tracing you're allowed to do exactly 1 time, and then go through the copath, you now have to go through a second double-headed arrow. So we have these 2 models, model 1 and model 2, one with assortment, one without. And as a quick example, I'll run through how to get the covariance for offspring phenotype with the non-transmitted paternal allele. So I'll start with model 1 with no assortment. To get the covariance between these 2 variables, we need to trace all the chains between them that don't violate the path tracing rules. So for this particular model, there are 2 paths that meet this criteria. And notice that both of them go through the father's phenotype, which is kind of intuitive. Without assortment, the only way that your father's non-transmitted alleles can have an impact on your phenotype is through their impact on his phenotype. So we get the product of this path, so 1 times F times 1 times half W, add it to the product of this path, and we get this simple estimate for the covariance. So you can see here this model is really simple. It's intuitive. You can visually see the mechanisms by which the alleles are acting on the phenotype. If we want to do the same thing but with assortment, we turn to model 2. So again, we'll trace the paths between these 2 variables, starting with the ones that don't go through the copath. So that's all of these. And again, most of them are going through the paternal phenotype. However, with the addition of assortment, NTP alleles are now also acting on the offspring phenotype through their effect on the transmitted alleles. And this is an effect that's entirely independent of the paternal phenotype. So in addition to those paths, we also need to look at all of the paths between these 2 that go through the maternal phenotype. So because of the rules where the copath resets everything, there are actually 36 unique ways to get from YO to NTP through YM. I regrettably counted them. But rather than figuring out all the products within each path and summing them together with the other paths, we can just implement some shortcuts and make our lives easy. So for example, we can say that the covariance between these 2 terms is equal to omega, so it's all paths connecting these 2 variables. And we can say that the variance of the phenotypic variance, all paths connecting ym back to itself, is equal to sigma squared. So if we use those shortcuts, estimating the covariance actually becomes really simple. It's now just equal to 2 delta G plus F omega plus F sigma squared mu omega. So even with assortment, this model is still super easy to utilize and provides really intuitive estimates for each constraint. Now, I won't go into too much detail with this because Yonggang will be discussing in the next session and also in the interest of time. But we have checked these estimates using a number of simulations across various scenarios, and we've been consistently finding that the expectations produced from our model line up really nicely with the observed values from the simulation, so that's great. All right, so next I'll be showing that our estimate of VF is unbiased, even when the polygenic risk score accounts for a small fraction of total genetic variance. So I'll demonstrate this using model 1 with no assortment. And again, I'll be implementing some shortcuts. So as before, sigma squared is phenotypic variance. We also have theta NT, which is the covariance between the offspring phenotype and both sets of non-transmitted alleles. Same for theta t with the transmitted alleles. So through path tracing in some algebra, we can get this constraint, and you'll have to take my word for it because there's not really time to demonstrate, but x, which is equal to the familial environmental variance, is equal to 2 sigma squared theta nt over theta t. So when the polygenic risk scores are standardized, these thetas represent the R-squareds of the child's phenotype regressed onto the haplotypes. So with that in mind, if the polygenic risk score is accurately capturing all genetic variants, then theta will be a perfect measure of the transmitted and non-transmitted alleles effect on offspring phenotype. But as we know, this is never the case. Polygenic risk scores generally account for a small amount of genetic variance. So instead of having these perfect measures, instead we have theta hat nt and theta hat t. So these are just noisy measures of true theta. However, the noise will be the same regardless of whether the alleles are transmitted or non-transmitted. So in this fraction here, the noise is effectively canceling out, meaning that the expected ratio of theta hats will be equal to the ratio of the true thetas. As a result of that, the ratio of estimated theta nt and estimated theta t will not be biasing this point estimate of x at all. Instead, it will only affect the standard error of x as a function of the variance for this ratio right here. So in short, we can get a full estimate of familial environmental variance regardless of how bad our polygenic risk score is for the trait. Okay, so with my last couple minutes, I'll go over a couple extensions of our model because I'm really excited about them. So I've been focusing a lot here on this particular model, but maybe we don't want to assume that parents are affecting their child equally. So we can easily allow for differential effects with this FP and FM here. In addition, I mentioned that the polygenic risk scores generally account for a small amount of genetic variance. So you might want to include full genetic variance by including these latent genetic factors here and here that incorporate the genetic factors not in this PRS. So visually, this model I know is a lot to take in, but if you can believe it, conceptually, it follows the same logic as the previous models I talked about, and mathematically is really similar in complexity. We're also working right now on developing models that use siblings rather than trios, which will make it applicable to a lot more data sets and is hopefully something down the road that we'll be able to use in the UK Biobank. So in conclusion, we created an accurate model of vertical transmission, which is really exciting. We can accurately quantify just how much of an impact parents are having on their kids. Our model can also account for assortment at equilibrium and disequilibrium. You can even use our model to test whether a trait has reached equilibrium, and provides an unbiased estimate of familial environment with only a polygenic risk score. And most importantly, I think, it can be extended to various situations to best fit the needs of your trait and data. We also hope that by using a structural equation modeling, we're allowing for direct comparisons between our model and other classic family models in behavioral genetics. So as a final takeaway, I think it's safe to say that one of, if not the highest priorities of VG research is to accurately estimate the effect of genetic factors on any given trait. And with that in mind, it's kind of hard to imagine questions that wouldn't be impacted by the confounding of vertical transmission with genetic inheritance. And while the exact degree of this bias will kind of vary from trait to trait, not sure what those were, but excuse me, I just heard a noise through my headphone. So this bias will vary from trait to trait. Being able to tease apart these factors using models that make as few assumptions as possible will definitely help us get closer to that goal of better understanding genetic architecture. So thank you all for listening. I want to thank my co-authors, my friends, my dog, and I'll take any questions that you have. I'm not really sure what to do next.
Wonderful. Thank you so much, Jared.
Yeah, sure.
That was a great first presentation. So if you'd like to ask a question, remember you need to go to participants and to raise your hand, and we'll unmute you to ask your question. Okay, Liz, you're first up. I will unmute you. Okay, go for it.
There, can you hear me now?
Perfect.
Okay.
Hey there.
Hey, that was so amazing and interesting. exciting
Thank you.
tool that we're going to be able to use. Have you thought about being able to include something like sex differences?
Do you mean for the offspring?
Yes.
Yeah, that I think is actually one of the bigger assumptions that we're making right now, is that the effect will be the same regardless of the offspring's gender. But that is something that we're trying to figure out how best to evaluate right now, how to make that change. It's been more difficult than you'd think, but ideally down the road, yeah, we'll be able to figure that out.
Thank you.
Sorry, the next question is going to come from Mike Neal. You should be able to unmute yourself now.
Hi, yes, a really wonderful presentation, and sort of brings back memories of my first BGA in the early 80s, where I presented models for genetic and cultural transmission using twins and their parents.
Cool. It's my first one too, full circle.
The interesting question then is, if you were to merge those two designs, could we see if we got corroborating evidence from a design able to distinguish phenotypic and genetic transmission in these two different ways? And have you any thoughts on a multivariate extension?
Yeah, well, to address your first question, do you mean merging the approach that they used with our approach?
No, actually, I meant more gen-epi kind of approach, using a design such as twins and parents that can disentangle genetic and cultural transmission in a similar way.
Yeah, I think similarly to my last answer, that's kind of one of our main goals right now, especially looking toward the UK Biobank. If we can combine both the sibling relationships and the parent offsprings that are in that data set, ideally it would really minimize the error estimates that we're getting and really improve the accuracy rather than having to rely on just trios or just siblings. And I'm sorry, what was the second part of your question?
I'm sorry, I'm not sure if I remember that. Well, multivariate extensions.
Yeah. That would be great to do down the road. You mean for multiple different phenotypes?
Mm-hmm.
We're thinking about that in two different ways. One, where the parental phenotypes differ from the offspring phenotypes and from each other. So we're hopefully going to have that in the near future. But we haven't really put much thought toward using multiple offspring phenotypes simultaneously, which I think would be really helpful, especially looking at relationships between things. I don't think it'd be too difficult.
Yeah, I think so too. Thank you. Great stuff.
Yeah, thank you.
Okay, so I've realized we have no clap track, so
thank you.
I'm going to return you, so you'll no longer be a co-host.
Okay, well, thank you, everyone. Nice talking.